Okay.
Yeah, yes, you may start.
Okay. Yeah. So, welcome everyone who's here. So, this is going to be a seminar, a series about F singularities, where we will talk about the some of the well-known concepts in with regards to the F singularities, namely some F regularity, F injectivity, F purity, F splitting. So, and there are ways to measure how far a ring is from these things and singularities. And yeah, we'll look at that in this series. So today we'll be talking about Frobenius uh, and also about Frobenius push forward. So that is going to be the key topic of this uh, lecture one. So notation is just R is Noetherian commutative ring with unity, and uh, characteristic of R is P prime. So recall that uh, characteristic of a ring R is defined as n, where the kernel of the map from Z to R is nz, n greater than or equal to 0. So by setting the characteristic of R to be a prime number, what we are saying is, in fact, uh, R is equi-characteristic. Equi-characteristic. That is R modulo M. So that is characteristic of R modulo M is characteristic of R is equal to P for all M maximal ideal. So this can be checked very easily because uh, characteristic of in general characteristic of R mod M divides characteristic of R, but in this case characteristic of R is P. Therefore, when a characteristic divides a prime number, it must be that prime number. That is why this is equi-characteristic. Yeah. No, no. Take R equal to Z. Yeah. Huh? Sorry. Uh, Z modulo P. No, R modulo M. So this is going to be the residue, not residue, the quotient field. R modulo M is a field, right? For M a maximal ideal. Yeah. Okay. So in fact, R is characteristic of R is P if and only if Fp, which is Z mod Pz, Z mod Pz is contained in R. Me say injects into R. And this is true from the prop by the definition of characteristics of R. So we can see that quite easily. So this is our uh, notation. And one more notation I would like to add is Q equal to P power E. We call this prime power, where E is greater than or equal to 0. So now we get to the first definition, which is the Frobenius endomorphism. Is this map F from R to R, where an element R is taken to R power P, and this is a ring map, and that is because f of R times S is R S the whole power P, which is R power P S power P. This is equal to f of R times f of S, and f of R plus S is R plus S whole power P, which is equal to summation P choose I, R power I S power P minus I, where I runs from 0 to P. And this is actually R power P plus S power P, since the binomial coefficient P choose I is divisible by P for all I from 1 to P minus 1. So the middle terms all vanish, and what you're left with um, are the end terms. And of course, this is just f of R plus f of S. So the Frobenius is a ring map. And now there are examples where we look at the ring R and the ring of characteristic P. One very trivial example is FQ, the finite field with Q elements, and F is the just the Frobenius map. This is an isomorphism of fields, and that is because F is injective, because this is a map of rings and FQ is a field. Uh, Hence, it is surjective uh, by cardinality. So both sides have the same number of elements, a finite number of elements, which is Q. And so if it is injective, it must be surjective, and vice versa. So yeah, yeah. What? Oh, oh no, no, no. I wrote this notation, right? So Q is a prime power. Q is equal to P power E. P is prime. Q is P power E. So we have defined, we know that finite field exists for all Q, which is a prime power. Otherwise, finite fields don't exist, right? Is that
I have
okay?
one question.
Yeah.
Uh, like if you take, so my question is characteristic of R modem can be zero for a ring R.
Characteristic of R modem Can it be zero? It could be zero, yes, but uh, we are not we are not looking for those type of rings. Like
That is fine. Like
if
in
characteristic
general,
of
you wrote characteristic of R modem divides characteristic of R. So if it is
uh,
zero, it does not make sense.
Uh,
so
I
if
think like
uh, if characteristic of R mod m is greater than zero. Okay.
So I have just one question. Can a ring of
Yes.
characteristic P
Ah,
uh, can have this property that characteristic of R mod M is zero for some n?
no, no. So if characteristic of R is a prime power,
Hmm.
then R is equicharacteristic. So characteristic of R mod m should be equal to P for all maximal ideal.
But it is not the case for characteristic zero, right? For characteristic zero, characteristic of
Yes.
R mod M may be P, right?
Yes, but P divides zero.
Yeah, that is fine. Okay, thank you.
Yeah. Yeah. That's why I wrote in general, characteristic of R mod m divides characteristic of R. When characteristic of R mod m is positive. But if we apply this result to the case we have, which is that the characteristic of R is a prime power. So characteristic of R mod m is something positive if characteristic of R itself is positive. Because what you're looking at is you have a map from Z to R mod m. So this map, the first map Z to R itself has a kernel of PZ. So this Z to R modem should have a kernel which is generated by some number. It cannot have kernel zero. So yeah, when does characteristic become zero? When Z injects into that Z into that ring. If Z to R itself has a non-zero kernel, Z to R modem should also have a non-zero kernel. It cannot have kernel zero, which means Z to R modem should have a positive characteristic. And that is the reason also why this map Z to R modem is the reason why the characteristic of R modem divides characteristic of R. But if uh, Z to R itself has like a characteristic as P prime number, it means that the Z mod PZ which injects into R itself is a field. And so the characteristic of R modem, if it divides a prime number, it should be equal to that prime number. And that is the whole point of this discussion.
Okay, okay. Thank
Okay. Yeah. So this is an example of um, Frobenius, which is an isomorphism. Hence, F is an isomorphism. Okay. Now, next is consider R to be FQ round bracket T, which is the fraction field of FQ square bracket of T. So claim is that maybe instead of Q, we'll just have P. So now the Frobenius from R to R is injective. Why? Because this is a field. So any map of ring starting with a field must be injective, but not surjective. So for example, T does not belong to image of F. Otherwise, we can write T as some F of uh, T, F of T power P divided by G of T power P because of the Frobenius, and F of T the whole power P is some T times g of t the whole power p, and the degree on the left is some p power e, while degree on the right is some p power uh, d plus 1, which cannot be equal. So these are two simple examples. Now, another not so difficult result is uh, R. We assume that R is uh, of characteristic P greater than 0, and all the Noetherian assumption is also there. Then,
Uh,
yes,
Abhiram,
yeah.
can you tell why the degree on the left is p to the e?
Oh, so this is a uh, pth power of a polynomial, right?
Yeah.
And when you take pth powers, all the intermediate terms, like this is just the Frobenius map on
Yeah, yeah. The
acting on f
Frischmann
of
frame,
t.
you can split them up. That's fine.
Yes,
For example,
yes,
if you take x square plus 1, it will become x square the whole power p plus 1 to
yes,
the whole power p.
yes.
So that is x to the 2 to the power p, right? Not p to the power e.
Oh, okay, okay. Sorry. Yeah, this it should be p times e, and p times e on the right is some p
Sorry.
times d plus 1. In either way, in either case, like
Yeah,
on
yeah,
the
yeah,
left
yeah,
you
yeah, that,
have a divisible by p, on the
yeah,
right
yeah,
it's not
yeah,
divisible by p. Yeah.
not a multiple.
Okay. So f is injective if and only if r is reduced. So this is a very short result. So suppose f is injective, let r be a nilpotent element, then r power n is 0 for some n in n. Let p, let e greater than or equal to b such that p power e is greater than or equal to n, small n. Then r power p power e is r power p power e minus n times r power n, which is 0, but r power p power e is f of f of f of r, which is just so this is precisely applied e times, and so but yeah, this is 0, implies r is 0 since f is injective. And conversely, if r is reduced, uh, then uh, like kernel of f is the set of all r in R such that r power p is 0, but this is just 0, which is so that is a very quick result on uh, when f is injected. Now, a natural question. Yeah. Hello. Yeah. Uh, I was going to, yeah, uh, yeah. I was going to talk about that, but yeah, you bet me to it. I'll talk about it immediately. So now we go uh, to a quick definition. We say that R is perfect ring if F from R to R is an isomorphism. Okay, so this is analogous to how we have the perfect field. So in perfect fields, the Frobenius is an isomorphism, which means you can take the pth powers of pth roots of elements, and an extension of that is the concept of a perfect ring. So now we have a very sort of like, this is a result which I did not expect. I mean, I was kind of just fumbling around it, but yeah. In fact, let R be a Noetherian ring as we have before of characteristic p greater than 0, then R is perfect if and only if F is surjective. So to answer both of Aditya's questions, surjectivity implies injectivity, and hence it's an isomorphism. So there is a sort of parallel, not a parallel, but not exactly the same in this following result of commutative rings. I don't know if you've seen this before, which says that if uh, phi from Hom R of m comma m, which is just the endomorphism, is surjective, if phi from this is surjective and m is finitely generated R module, then phi is an isomorphism. The a very nice part of about this result is that it does not use Noetherianness hypothesis. This is true for non-Noetherian rings too. Noetherian rings. Anyway, a similar kind of result happens here, that if the Frobenius is surjective, then it automatically guarantees isomorphism. There is a caveat though. Here you need the Noetherian hypothesis. So proof. So this is clear because perfect implies surjectivity. So we just have to prove this implication. Let P be in spec R. Apologies, I will use the notation P for prime ideals, but sometimes it looks like the characteristic. It just, yeah, from the context, it should be clear. Then there is a map from RP to RP. This is also the Frobenius map. This is induced from the Frobenius map F from R to R. And that is because if you take any multiplicative, so I'll just say this in words. If you take any element in R minus P, that element's power is also an element in R minus P. Therefore, it takes units it takes the multiplicative set to multiplicative set on the other side. Therefore, it factors through the localization. And hence, and so this is induced from this, and it is surjective by hypothesis. Same reason. So once the units go to units, surjectivity is still preserved. And another thing is that um, so okay, now what is FP of this PRP? This is going to be P power P RP. It's the pth power of all the elements in the prime ideal. And my claim is that this is actually equal to PRP. Why? Because first of all, it takes so because FP so F of PRP is contained in PRP, and if we look at elements outside PRP, it is contained in it is outside the maximal ideal. So since F is surjective, the elements in PRP must have pth roots. We are using the fact that it is surjective. But does this remind you of something? Okay, that's Nakayama, by the way. So by Nakayama, PRP is 0. This implies RP is a field. Okay, right. So in particular, what? So PRP is which one? So P power PRP, yes. So this is just if m is equal to m, then m is 0. Nakayama. Yeah. Okay. So this is by Nakayama, PRP is 0. Therefore, if the maximal ideal is 0, then it must be a field. So in particular, RP is
Abhinav,
yes.
here what is the capital M? What is the module here? It is the
Oh, here it's PRP. So PRP is the maximal
max.
ideal in
Yeah, PRP is the maximal ideal. What is that
yes.
module M in the when you apply the Nakayama here in this
So I'm
situation?
applying the result for this module itself. So PRP. So okay. Um. So this is what I'm saying. So P power PRP, right?
Hmm.
RP is contained in P square RP, which is just P times PRP. But this
Ah,
is
okay,
just
okay. Now,
PRP.
now. Yeah. Okay, okay. Yeah.
Okay.
Yes,
So
yes.
therefore, P times that is equal to PRP. Therefore, PRP is 0. Okay. So in particular, because now we have that RP is a field, therefore RP must be reduced for all P in spec R. And what do we know about reduced property? Hence, R is reduced because uh, reduced is a reducedness is a local property. And this implies F is injective. Okay. Yeah, I was just thinking about the result yesterday and it looked very cool. Like, so I just wanted to include
Yeah,
this.
it's a nice proof. Yeah.
So now there is a very um, so now I just want to make a claim that um,
Earlier you said like it is also true for non-Noetherian rings, right?
Oh, no, no, no. That result was the different case. Like, I was talking about the form R of M
Yeah, yeah,
comma M.
yeah, yeah,
But
yeah, yeah.
this
Not
is
even not the Frobenius map. It
not
is
the
some random
Frobenius one
endomorph.
because we are
Yeah,
using Nakayama. So we need
yeah, yeah.
RP
With it.
to be, yeah,
Yeah.
Noetherian. So
So
for it to be
earlier, what
finitely
you
generated.
yeah.
That was a different result. I think this was a
So
result
there,
on,
yeah, yeah. So if I recall, like you said, like if it is a random endomorphism and M is a finitely generated R module,
yeah,
and if the endomorphism is surjective, then you can say it
it's
is
a
an
nice,
isomorphism.
yes.
If it is the Noetherian situation, and you said like the result is same true also
No,
for
no.
non-Noetherian case.
Yeah, that is for the endomorphism, right?
Uh-huh.
Endomorphism in as like of module. Now this is like Frobenius, but the Frobenius is a ring
Okay,
morphism.
okay, ring homomorphism. Sorry, sorry.
Yeah,
Yeah,
it's
yeah,
a
you're
ring
right.
morphism.
Okay,
So
okay,
there is a
okay, okay,
subtle difference. Okay.
okay, okay. Yeah.
And in fact, the Frobenius need not be a finite map. In fact, if it is a finite map, we call the ring as F finite. We will look at it in the upcoming lectures. So the exercise is that is this uh, result valid if R is not Noetherian? As I wasn't able to check, so yeah, it's a question, not an exercise question. Okay, so thing is, so another definition, which is not particularly a definition. So the iterated Frobenius Fe is the map from R to R, where R is sent to R power P power E, which I'll just call it as R power Q, uh, where Q is P power E. So yeah, uh, and then another definition is let I in R be an ideal. We define the Frobenius power I square bracket Q as the ideal generated by x power Q for all x in I. And in fact, if uh, so, in fact, I Q is actually f of f e of I dot r. So yeah, this can be checked quite easily. And if I is generated by elements f1 to fr, then I square bracket q is also generated by f1 power q up to fr power q. Okay. And uh, I square bracket q is contained, but not necessarily equal to identity.
Even if the ring is characteristic P, this is not true.
Oh, this is for characteristic periods, right? So these are positive characteristic
Okay, okay.
guys.
Yeah, yeah, yeah,
Yeah,
yeah.
yeah,
Okay.
yeah.
So is there
So
any rings like class of rings where like this Frobenius power and ordinary power will coincide?
no, because again, if the ideal is principal, then of course this equality must hold. Uh so let me just write not necessarily equal. Of course, other than when I is principal. Because when it's principal, it's just generated by one element and the no ordinary power and the Frobenius powers are the same. But if it is generated by two elements, say let R be K, uh, just R is say FP x comma y, and I is going to be the ideal x comma y, then I square bracket p is the ideal generated by x power p and y power p. But I power p is just all the monomials of degree p. So x power p minus 1 y, so on x y to the power p minus 1 and y to the power p. So I square bracket p is not equal to I power p. Is this okay? Okay. So now we go to the most important topic of this lecture, which is Frobenius push forward. Now, this is very important because it will be used repeatedly in the proofs later, and so it makes sense to cover this in detail. So when we have a ring map, phi from A to B, we have a module structure on B via phi. That is, if say A dot the action is defined as phi of A times B for all A in A, B in B. Now, in the case of Frobenius, both the source and target are the same rings. So this leads to some confusion. Uh, Primarily, uh, when we have a module structure on P, it is also the same structure which the image of P. So this is the same as the B, the action of P of A, which is contained in B via inclusion. So in the case of Frobenius, one way to remedy this is to look at the inclusion. F of R inside R, that is R power P inside R, and in general, the iterated Frobenius can be written as R power P power E inside R. But this, but in these cases, the base ring is R to the P to the E, not R. We don't want that. We want the base ring to be R so that we can look at the R modules and then extend it where in some way to the Frobenius action and all that. We don't want the base ring to be R to the P to the E. So that's where Frobenius push forward comes in. Let us denote the target ring in the Frobenius map as F E star R. In other words, F, the Frobenius map, is a map from R to F E star R, where because this is Frobenius map, it sends R to the element R power P power E. So, okay, the elements of F E star R are precisely F E star of R for all R in R. Yeah. I don't know why this connection got cut. Continue. Start. Sorry, was this visible? Uh, like, so, yeah, okay. So, yeah, so these things were okay, right? So, why we are looking at push forward instead of just looking at the inclusion? So, we want the base ring to be R and not powers of R. So, we are defining the target as a separate ring. We call that the push forward of R. And the elements are precisely this Fe star of R, and uh, there is an isomorphism uh, from Fe star R to R. Okay, no, this is not true, but yeah. So these are precisely the elements in the Frobenius push forward. Uh, right. So if we look at the previous example here, uh, the reason why I mentioned this ring map is that the structure A action on B makes this ring map an A module homomorphism. So let me write it in a different color. Uh, so the A action makes P an A module homomorphism, which we can check very easily. If it is just A dot A prime, uh, it's going to be because it's a ring map, it is phi of A times phi of A prime, but this is just A dot phi of A prime by the definition of this action. This is action, right? So here we have this. So phi of A dot A prime is A dot phi of A prime. And this, the natural action makes P an A module homomorphism. So if we define the target ring as a separate ring instead of looking at it as R, this makes Fe an R module homomorphism, because if R comma R prime, belong to R. Maybe I'll just use yes. Then F E of R times S is uh, so it takes R to F E star of uh, R power P power E. Um, oh, okay. So wait, yeah. So this is S to the P to the E, and this is just R dot F E star of S to the P to the E. I realize now that I have not defined what the action on this is. So the action on uh, FE star R, the R action on FE star R is via the Frobenius map FE, like how we defined before. That is R dot FE star of yes is precisely FE of R times FE star of yes. And what is FE of R? It is uh, just using this definition. It's just by definition in this. So R is taken to FE star of R power P power E, right? So this is FE star of R power P power E times FE star of yes, which is FE star of R power P power E dot S. So this is the R action on FE star R, and applying that to this FE, we see that it is FE star of R power E times S power P power E, and we can take R outside, which just becomes R dot this thing. So, uh, so this is just so this is R dot FE of S. So this is the action that we are interested in. That we want to make the target of the Frobenius as an R module. And this action is what makes the Frobenius homomorphism very interesting. And we can also define, let M be an R module. We define Fe star M as the set. Fe star M is precisely the set of elements Fe star of M for all M and M, and Fe star R acts on Fe star M by the very obvious action. Fe star of M is Fe star of Rm for all. Yeah, I think this should be. Yes. This action is not very it looks natural, and this is not very interesting because this is similar to the action that M of M as an R module. The more interesting action is since R acts on Fe star M via the Frobenius Fe as R dot Fe star of M is what? Fe of R times Fe star M, and this is Fe star of R to the P to the E, Fe star M, and this is Fe star of R power P power E. So now for any R module, we can look at that R module as an R module via the Frobenius, Fe, iterated Frobenius. And this is the more interesting action which makes this subject very interesting. So I think I mentioned about most of this stuff. Okay. And finally, if F is from M to N is an R map, R mod homomorphism, then the push forward map from Fe star M to Fe star N is also very natural. Fe star of M is getting sent to Fe star of F of M. So yeah, this makes Fe star blank functor R mod to R mod to Fe star R mod, a functor. So functorially, just the definition of Fe star R and Fe star M, uh, it makes sure that the underlying abelian group is the same, just the action changes. So we expect that this functor has some nice properties, and in fact, it has nice properties. Number one is Fe star blank is an exact functor. And number two, there exists let W in R be a multiplicative set.
I have one doubt.
Yeah.
So, so you are thinking Fe star are same as the ring R, but you are giving a module structure here by Frobenius map, right?
So Fe
Nothing else.
star R is the so uh, let
So
me
by the Frobenius map, you are giving module structure here, right?
so Fe star R is precisely Fe star R. This is just symbolic. So the element in Fe star R, I'm writing it as Fe star of small r. Uh, yeah, this is by definition.
Yeah, and it is an R module.
Uh, it is a ring. It is a ring.
So this
It is a
that R
yeah.
module structure. So you have a map from R to R, the Frobenius map.
I'm
So R,
looking at that.
so
Yeah.
yeah, so by that Frobenius map, we are giving R
No.
module structure to R, right?
So that's what I was. Uh, the motivation for this comes from this fact. When we have a ring map from A to B, we have a natural A module structure on B. But here the Frobenius takes it is a map from R to R. If we look at these two R's to be the same, they're not the same because the Frobenius action is not the identity map. So we want to write this target in some other as some other ring. So you could call it yes if you liked it. But the notation that we use is F star R. So that is this F star R. So the target, I'm just writing it in a different, I'm writing it as a different ring, a symbol. And this is a ring, and Fe is a ring morphism. And the Frobenius takes R to R to the power P, R power P power E. So that is just the same in a different language. And this natural structure, now Fe star R, uh, the module structure, the R module structure on Fe star R is via this Frobenius map. That is R dot Fe star S is how you how R acts under Fe, and then I'm multiplying that with the element this Fe star S. But Fe of R is just Fe star of R power P power E. That is by the definition here. And so, and this is just a ring product. So ring product is just the natural way that you expect. So R dot Fe star S is Fe star of R power P power E times S. It is not Fe star of R times S. And uh, so this makes so, so this makes Fe and R module homomorphism, because if you take two elements R dot S and you apply Fe on it, you can see that that is R dot Fe of S. So yeah, now we can look at uh, the target ring, and uh, so you could very well say this is yes, and any S module must be an R module via this action. And those are things that we've already studied before, right? So that is called the restriction of scalars, and there is something called extension of scalars. So we are applying that theory here. So we want a different symbol here. We don't want the same R. That will confuse people. So we are calling it, say, some yes, and then this being the uh, restriction of scalars, extension of scalars. Is that okay?
Yeah.
Sorry? Oh, you want? Uh, no, 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 no. So yeah, I'll come to this proof. So let W and R be a multiplicative set. Then uh, the map, which we will define as psi from Fe star R localized at W to maybe not as so Fe star of Rw, which takes an element Fe star of R divided by W and sends it to Fe star of R modulo W power P power E, is an Rw linear isomorphism. So I don't have the time to prove the second part in full. I'll just give the map and you can check that they are inverses. So for first one is easy to check. So let 0 to m prime to m to m double prime to 0 be an exact sequence of R modules. So this is F and this is G. Now the underlying so F E star of F, and so the underlying M is isomorphic to Fe star of M as abelian groups, and the maps F E star F is the same as F. The elements that it takes, they don't change. In fact, the only thing that changes now, uh, so consider, okay, after applying F E star of blank, we get the same thing. So 0 to F E star of M prime to F E star of M to F E star of M double prime to 0. This map is F E star F. This is F E star G. Now, the underlying maps, they don't change because an element in this Fe star of some M prime, this is taken to Fe star of F of M prime, which means the kernel of this is going to be 0 because F has kernel 0. Similarly, the co-kernel of Fe star G is 0 because the co-kernel of G is 0. Hence, kernel of Fe star F is 0, co-kernel Fe star G is 0, and image of uh, Fe star F is kernel of Fe star G. Hence, this is an exact functor. So all this push forward it's doing is it's changing the action from an R module action to Fe star module action, Fe star R module action. So note that Fe star changes R module action to Fe star R module action and does not change the underlying abelian groups and maps. So that is why this is exact. The push forward is an exact functor. And two, so first you have to check that it is RW linear, but that can be checked by making sure that the units, so the multiplicator is a W sent to units on the other side, so it factors through and you get an induced map. And then, so I'll just write it here, check that phi, which is a map from, so phi is a map uh, from F, where is phi? Okay, so phi is Fe star of RW to Fe star RW, where the element R by W is sent to Fe star of RW power Q minus 1 divided by W. So check that this is inverse is P is inverse to sub. Okay. Also first. P is well defined and RW linear. So there's a final remark that I want to make, uh, which is that uh, F star R has an alternate description when R is reduced. So I just want to briefly state why this is true and what that description is. So remember that we were somewhere before we talked about this. One way to remedy this is to look at the inclusion F of R sitting inside R. So R power P is sitting inside R, and um, but that is one way of looking at the Frobenius action via this inclusion. But this gives the base ring as R power P power E and not R. But what if we can take the P power E at the roots? What if we can take uh, the P power E at the root of this inclusion? Then we are going to get something like R sitting inside R power 1 by P power E. And then our base ring will be R, and we can look at this Frobenius push forward as this ring R power 1 by P power E. So if that happens, then we are in nice territory. But that doesn't happen always. It does happen when R is reduced. So the reason is because pth powers, because uh, pth roots uh, don't exist if R is not reduced. You have nilpotence, and nilpotence will mess things up. But if R is reduced, then uh, we can look at a nice description. So how? First, R uh, R sits inside associated P in associated prime of R localized at P. So this is a very uh, it's a very natural statement, R by 1. That is because these are all the associated primes, and any element must be non-zero in at least one of the RP. And if R is reduced, R associated primes of R is minimal primes of R. Moreover, if P belongs to minimal prime of R, then RP is a reduced local ring of dimension 0, hence a field. So we write RP as K of P, the residue field of at P, R at P. So we have inclusions R, which is contained in the finite direct product P in min R, K of P, which is contained in the product K of P, the algebraic closure. Now, note that as we saw before, these are all residue fields. So they must all be characteristic P. So these algebraic closures are also characteristic P. Let's just call this K. And so in K, we can take um, p power e roots. That is, so now we can define r power 1, I'll just write this r power p power minus e is defined as the set of all a in k such that a power p power e belongs to r. So, and then there is an isomorphism of rings, which I'll just call psi e from r to r to the p to the minus e, where an element r is sent to its pth roots. Its pth root. So yeah, you can check that this is an isomorphism of rings. That is by via the definition. Okay. So, but still, we have not mentioned why this mimics the Frobenius action. So, under this isomorphism of rings, the Frobenius action Fe from R to R and the isomorphism psi E is maps to R power P power minus E. This is sending R to R power P power E. But this is getting sent to psi E of R power P power E, which is R. The P power E root of this element is R. Hence, psi E, so is identity on R. And so R sits inside R power P power minus E via Frobenius. So not this is a bit misleading, but uh, this is the Frobenius action. Now, what did I say about the Frobenius push forward? I told that Frobenius push forward is whatever is in the target. The target is this. So this is what we wrote as Fe star R. And therefore, Fe star R is isomorphic to R power P power minus E as rings. And this isomorphism is given by Fe star R, R power P power minus E, an element Fe star R is taken to um, R power P power minus E, and in the other direction, an element X is taken to its power. So Fe star of X power P power E. So this is an alternate description of the Frobenius push forward when R is reduced. But the thing is, we typically use the Frobenius push forward functor instead of this inclusion because that is functorial and it is easy to keep track of. The inclusion, it's a bit cumbersome because when you have like iterative Frobenius, uh, many composition of just maps, that may give it does not translate well when we are looking at inclusions, but it translates well when we look at them as uh, the push forward functors. So we functors means that it stacks up nicely. So that is the first lecture. So that's what I've prepared for today. And in next lecture, I want to talk about the integral closure and tight closure, how they are similar, and then possibly just stating Kun's theorem. And yeah,
Uh, Viram, can you move a little
yeah,
forward? So there in the remark when
sure.
yeah.
Yeah,
So there when you said like the R sits inside the product of R